A communication problem with the computer in here. Better. Often happens at the start of the academic year, the computers are cleaned during the summer of everything that was on them before, and then when you first come to use them, they don't work. So while this is booting up, my name's Steve Bull, I'm the module leader for the Materials and Fabrication module. This module is shared by materials engineers and pipeline engineers, and that's the reason why it has quite a funny structure. We have lectures this week, and then there are 2 weeks when the pipeline engineers go off and do other things, and then we all come back together in 3 weeks' time to have the lectures for the rest of the session. So if you think your timetable looks a bit odd, it's because of the week-long modules that the pipeline engineers have to do at the start of the course. So this is like an introduction before the pipeline engineers get an introduction to the subject. So it's a bit different, perhaps. Right. So there are 3 lecturers on the course. There's me, I'm the first person there. Dr. Euler, who will mainly be lecturing you in lab classes, where we'll go through some of the things that have gone in the lectures in a little bit more detail. He'll also do the next lecture because I can't do it. Timetables don't always work. And then Professor Gibson. Now, Dr. Euler and I will basically be talking to you about steel, and steel for pipelines, and how you make steel, and how that steel is used in pipes. And Professor Gibson will talk to you about plastic pipes, which are the main pipes that are used in the industry. Now, this course was originally started by the gas industry to talk about gas pipes. So we're not going to talk about water pipes, we're not going to talk about oil pipes, we're going to talk about the hardest ones to do, gas pipes. Because obviously, when you have gas, you have extra problems that you don't have in these other systems. And what we're going to talk about is how you make the materials, what the material is. So saying steel doesn't mean anything. You know, what steels are used in the pipes, what plastics are used in the pipes, how that material is converted from raw material into a pipe geometry, how those pipes are then laid out along an access way, which you can see here. We talk about the spread technique for pipeline manufacture, and how you weld those pipes together to make a pipeline. So it's all about going from raw material through to the finished product. As well as the pipes, we'll talk a bit about the fittings. So you can see some bends at the top there, and a T-piece here, and a manifold. So there are lots of things that you have to put onto a pipeline, which are also made of steel or plastic, and they're not the same. And so how do you deal with the fact that you have different materials coming into contact together? How do you make it very good? Because if you get it wrong, for a gas pipe, these are the sort of things that can happen, and you don't want these sort of things to happen. So that's an unzipping weld failure. There you can see that flat sheet was originally a pipe, and a crack has run through that pipe, and actually you can get cracks in pipes if you don't do it correctly, which can run 1 kilometre or more. You don't want to have to replace 1 kilometre of pipe for one small failure, so you need to get things right. You can get a gas explosion. That's actually a test explosion, so that's not too bad, but you don't want to have a gas leak and spark and a big problem. And then if the explosion happens on a smaller scale, you can actually throw the pipe a long distance, and anybody that gets in the way is not going to come out of that walking, let's say. So the person with that Chevrolet truck was very lucky that the pipe landed on it when it was in the car park and not when they were driving along. So that black and white failure from the UK is a gas pipe explosion from a long time ago, and it was failures like that which made us start to look at how we improve the materials and improve the manufacturing process so we didn't get these failures. In this country, most gas pipes onshore are buried under the ground because we don't want to have that sort of failure. But there are times when you're crossing a bridge, crossing a river or something like that, where the pipes are exposed to the air, and that's okay. They have to be specially designed in order to deal with that. If you're in Canada making a gas pipeline, it's almost impossible to dig into the permafrost, to dig a trench to put these things in, so the pipes run on trestles above the surface. And so you have to be much more careful when you're designing those, particularly because the ambient conditions, the temperature is very low. And you may not realise, but steel becomes more brittle as the temperature drops. And this ductile to brittle transition is something that we have to deal with when we're making a pipeline. So the aim of this module is to teach you a bit about the fundamentals of metallurgy and material science, to show you how you need to know that to understand the welding procedures and the design procedures for the pipes, and to actually give you an understanding of why procedures are set up the way they are. So if you're going to be a pipeline engineer, you probably won't need to know all these levels of detail, but you might need to know why a welding engineer works so hard to make sure that the procedures are kept to. For the materials engineers, you'll need to know how you modify the properties of a basic material, steel, to be suitable for this particular application, and for the welding and the joining, what effect that has on the materials that you're using. And so both of those will come up as part of as part of the module. There is an exam in January for this module, and there is also an assignment on materials and metallography, which will come up and be released to you by Dr. Euler, and that will probably be due before Christmas. We haven't set the date yet, so it's going to be towards the end of the course. But he will introduce that assignment to you as part of the practical classes. So this first week we'll just have lectures, and then, as I said, there's this 2-week gap, and then we'll start off with 2 lectures from me, 1 lecture from Professor Gibson, and the lab class from Dr. Euler, and that will run through afterwards. So, what I want to do this week is give you an introduction to the subject area. So we're going to look at what properties do we need to specify for pipeline materials. Because if we've got to write an order, if you're going to a pipe mill and say, I want 1,000 metres of pipe, what do you put on the order? What do you have to say? What are the characteristics of that pipe that we have to write down? And there are 3. Strength. There's an internal pressure in the pipe must resist that internal pressure, so it must be strong enough. Toughness, that's resistance to cracking. If there's a defect in the pipe, the crack mustn't be too bad. It must be stable, but it mustn't grow. We'd rather these things leak before they break. And finally, weldability. You're going to have to make a pipe in short sections and join it. So you're going to have a material which can be field welded, and not one that requires special conditions and very expensive gases and things like that. So if we think about it, we've got to specify a material which is capable of delivering the requirements in all of these cases. That sounds easy. Let's look at that and unpick that. So strength. Most people in the industry know about mechanical tests because they will have to do that as proving tests all the time. And the simplest test that you can see here is a standard stress-strain test where we take a metal test piece. In this case, it's a cylindrical bar with some end pieces on it. And we pull it in this test frame, so we stretch it, and we measure the force. And what you can see also on this picture is this thing here is called a clip gauge. So you fix that on, and as you pull it, the clip gauge opens up and it can measure the extension. So you get a force versus extension plot. And if you know the original area, force divided by original area gives you stress of the sample, cross-sectional area. And extension divided by the original length gives you strain. And that normalises for different sizes of sample. And you end up with a stress-strain curve. So most steels that are made for pipelines, particularly the old normalised steels, the original pipeline steels that were developed in the 40s and 50s, they have this sort of stress-strain curve. So you get an elastic part, and then you get some sudden wobbles, serrated yield point they call it here. And then you get work hardening, and the stress will go up to an ultimate strength. And at that ultimate strength, you get what's called a plastic instability. So the material, instead of being a cylinder, starts to neck down locally and become thinner. And then the stress drops, but actually the real stress goes up. The engineering stress, based on the original area, drops, but the real stress, based upon the actual area, goes up. And then finally you get fracture. Now this looks good. The real key points are the ultimate strength and the yield strength. Yield strength is easy to measure on this case because we've got all these serrations. We can see the spot where that goes down. Unfortunately, when we design, what we want to be is in this region down here. We don't want to see any of this at all. But if there is an overload or if there is anything that causes problems, we may see stresses in these high areas. We don't want it to fracture. So this difference between this point and this point is, if you like, the safety margin that we've got for overstressing the material. Now that's an old steel. If I took a piece of pipeline steel from today, it would look something like this. And by the way, if you go onto the Blackboard system, you can download the PowerPoint files here. So don't need to write everything down. So the stress strain curve of a modern controlled rolled steel, which is used in the manufacture, the steel composition might be exactly the same as in the previous case, but it's been prepared by the steel mill in a different way. It doesn't show that yield drop. The rolling process that is used will remove that serrated yield. And so there's a gradual transition from the elastic behaviour into the work hardening behaviour. The other thing you'll notice is that the yield stress, which is defined in this case by a constant strain offset, so here's the elastic part of the curve. You take a 0.2% strain, draw a line parallel to that, and see where it crosses the curve. That's a way of getting an unequivocal, easy to define yield stress. Difficult to decide where this diverges from the linear portion, so that's why we use that. Anyway, this yield stress is much closer to the ultimate tensile stress. So if you like, the safety margin that we had in hand with the material is much less, but the strength is much greater. So we've got a material which has got much better properties, but our extra strength in hand is much less, so the safety limits are much more difficult. And sometimes we therefore try to define this yield strength divided by tensile strength ratio, the so-called Y over T ratio, as another parameter we might want to specify. We'll specify yield strength, we'll specify the ultimate tensile strength, and now we can specify this ratio as well, just to make sure that we have something which is as safe as possible and as well defined as possible. So if you're going to a steel manufacturer, you don't just ask for a yield strength, you ask for a range of parameters that have to be delivered in order for that steel to be acceptable. Now why is this important? Well, because the basic calculation that we do about strength in a pressurised pipe comes from Barlow's formula. So if you imagine a pipe, you can see here, of diameter D and wall thickness T, and the assumption in this equation is that the pipe diameter is very much greater than the wall thickness. Then the stress in the pipe wall is the pressure times the diameter divided by 2 times the wall thickness. There are very many proofs in mechanical engineering textbooks about this, but that's a very standard result. Now sometimes you'll see PD equals 20T, and that's just because the units are different. The equation is exactly the same, but if we put the stress in bar, 1 megapascal equals 10 bar, so you get a factor of 10 appearing in the equation from the two. So you notice here I've put the units, and the units of stress are pascals, or 10 to the 6th pascals, megapascals, which is just the same as newtons per millimetre squared. So if you measure the cross-sectional area in millimetres squared and you measure the load in newtons, you can get the stress in megapascals directly. So if we measure everything in millimetres, it becomes easy. The oil and gas industry, because it's got a lot of US parts to it, is very good at using mixtures of units and not always the SI units that we would like to use. So be very careful when you see an equation what unit set has been used, because they will mix bars. I've seen equations which have pounds per square inch and meters in the same thing. So that gets very confusing after a while. So always, if you're going to use an equation, write the units down. And if you're doing the exam at the end of the case, I'm very big on that. If you don't put the units down, you don't get the marks. So the other thing I like is not too many significant figures. If there's 3 significant figures in the data, no more than 3 significant figures in the answer, otherwise you'll get no marks. Because you can't have an answer more accurate than your input data. Anyway, we've got this equation here. So if we know what the pressure of the pipe is, And if we know what the material is, we can fix things like the wall thickness. The diameter is often dictated by the volume of product you want to flow along the length of it. So we use these equations as part of the design process if we have reasonable materials parameters to do it. Now we wouldn't just field the yield stress in, we'd have to think about this in a bit more detail. So we usually have what's called a design factor included in our equation. So the design factor that I use is the stress in the pipe wall at the maximum working pressure divided by the minimum specified yield strength of the pipe. So the minimum specified yield strength is a measured value. It's not an average value, it's the minimum value that you would get from your tests. And that's very important because we don't want things to fail. So we don't want to use an average value where the chances are things will be smaller than that. We want to use the minimum value. And then we multiply that by some factor, or in this case we're dividing by a factor just to say what we would want. So the stress in the pipe wall sigma then has to be reduced, or has to be increased to get up to the yield stress. So way of looking at that, we've got the stress strain curve here, S. This one's got the yield drop, so it's an old steel. We can see that the yield stress is marked there, but we would actually design at a fraction of that, 0.72S or 0.3S, you can see there. So those would be the design limits for the stresses in that particular material, and it's less. And if we do that, everything should be in the elastic range, and we always design with things in the elastic range. And you can choose different safety factors, different design factors, depending on circumstances. So typically, the design factor we use for buried cross-country land pipelines where everything is out of the way, no people near it, is about 0.72, maybe to 0.8. So you can use pipes near their limits under those conditions. Proximity land pipes, that's things that go near houses or roads or things where there might be some damage. We will drop that design factor typically down to 0.3. For very thick pipes, so wall thickness greater than 19 millimetres, I put 19.05 because it comes from a standard, that's what they chose. You can actually put that safety factor up. So if you've got a really heavy wall pipe, generally they're safer than the thin ones. At stations, that's things where people might go but don't usually go, so pumping stations, pig traps, compressors, all of those sorts of things. We might have a higher safety factor than the minimum because people go there, but we don't go right down to the lowest. Subsea pipelines, because of the external pressure, they're actually a lot safer intrinsically. So we operate closer to the yield stress, and the safety limit goes up. The exception being on risers, because a riser might come up in close proximity to workers, so we would tend to use a slightly lower design factor. And you can argue that these are safety factors. The lower this value is, the more safe you're trying to operate. Is it safe? Well, no, not necessarily, because it depends on the defects in the pipe. But this is saying, on average, taking the known properties of the pipe, this is the best calculation we can do. And these safety factors, design factors, are taking into consideration everything that we don't know about when we do the actual design. All the things that might affect our results, but we don't know about them beforehand. And they've been worked over the years to try and understand how the industry works and choose appropriate values of these design factors so that everything is going to be okay. Right. How do we define the materials then? Well, the American Petroleum Institute, API, has a standard line pipe specification. It's the 5L specification. And there are various different grades of steel that can be used to make line pipes defined in this specification. And here is an example. You can see grade B, which is really water pipe, is where things started up, and then the grades go, X grades go upwards. And if you look at that, the tensile strength goes up a bit, but there's an almost linear increase in yield strength. And there should be, because the grade, the number after the grade, is the effective yield strength in KSI, or 1,000 times KSI. So it should be proportional because that's the way it's been defined. So basically the different grades of steel that you can get from the API are really designed based on their strength. Doesn't say anything about composition, doesn't say anything about how you achieve that strength. They're just designed on the basic strength, which you can tell by the number. So up to about X80 are specified and widely used. You can get X100 and X120 and even X200, but they are experimental grades. They're very rarely used. I think X100's been used on one set of pipelines in Canada, and the Japanese have produced it, been trying to sell it for some time, but it's the industry moves very slowly. So in this country, X70 used to be the limit, and X80 was unusual. Now X80 is quite widely used, but that's about where we've got. So X100 is not there yet. No. So, yeah, yield strength of the steel in KSI, the 80. So that's fairly straightforward. That means that we can guess what the mechanical properties are just from the grade of the steel. For onshore pipelines, grades up to X70 are commonly used. As I said, in the UK we've put some large gas distribution pipelines around the country. Now we've got a lot of gas-fired power stations. And the spine pipes, the big pipes that deliver the gas around the country by Transco, are made at X80. And that's been really in the last 10 years or so that we've started to do that. But most of the installations are less than that. And if you ask me the most common grade, it's probably X65 around the country. As I said, X100 and X120 steels do exist. You can make them more expensive because they're a bit more highly alloyed, but nobody uses them yet. Though TransCanada have been trying them out. There are various reasons why you might. If you were in a very cold country, if you can modify the steel specifically for its ductile brittle transition behaviour, you might want to do that more than spend the extra installation money dealing with heavier pipes. Because if you've got a higher grade steel, the wall thickness of the pipe will be smaller and they're easier to transport. Some people like that as a way of doing it if you've got to transport over hard to run. X65, commonly used for offshore pipelines. Certainly in the North Sea, where most of our gas comes from, everything was worked out for X65 when the gas exploration started, and X65 works, so why change something that works? That's pretty much why it's there. And you have to get a higher degree of confidence in your materials if you're going to put something offshore, because if you put it on the bottom of the sea, you can't go in and repair it very easily. It's very expensive. So we tend to use very conservative, very old-fashioned maybe, but tried and tested methods for working there. Now, of course, the Americans have a standard, there's an international standard, and it's almost the same, but not quite. So the European standard 10208 and the ISO 3183 are just the European and international versions of the API 5L. But because standardisation people like to work in more straightforward systems, they metricate the API 5L versions and they convert them or round them to the nearest 5 megapascals. So an ISO 3183 and an API 5L steel are not quite the same. They're almost the same, but they're not So if you're working to one standard, make sure you're working to that standard and not the other one. Know which one you're doing. So if you take API 5L X80, if you work out what that is in terms of KSI and then convert that into megapascals directly, you'll get 551 megapascals yield strength. But if you look at the international standards, the standard for X80 is 555 megapascals. So it's nearly the same. And frankly, it doesn't really make a great deal of difference when you do the calculations. Because if you're worried about 4 megapascals on 550, there's something seriously wrong with the design process. ISO 10208 contains a limit on the yield stress to ultimate tensile stress ratio, which is more conservative than those given in API 5L, typically around 0.9 as opposed to 0.93. So what that says is that we don't believe in Europe that you can go as close to the limit with these materials as the American API 5L system will say. You need that extra work hardening in hand to allow for overstress beyond the yield stress limit. It's not a big difference, but it can be significant in some cases. So that's one of the things that I think there is a difference between the standards in and the ISO standard is marginally better. But again, it's not a big deal. And so here's the sort of information that you will get. So you'll have a table and you'll have the API grade, the EN grade, the yield stress, the tensile stress, and those are minimum versions. The ratio of the two, and the elongation, so that's how much you can stretch the steel bar before it breaks. And this is an American set of data. The comparison therefore has the megapascals numbers, the ISO numbers in the brackets after the American version. And you can see that the differences in the grades are small. So if you take grade B, for instance, you can see that 241 has gone to 245, 413 has gone to 415, 0.93 has been reduced to 0.85, or 0.8 to 0.85 in most cases. But they're still the same steels. So you need to know, as I say, if you're looking at materials, which standards is the company working to? And just make sure you do all that. The elongation should all be about 20%. And as we go up in strength, the material becomes more brittle and that elongation number comes down. And one of the reasons, therefore, that we were worried about going to these higher strength grades is that their susceptibility to fracture and their toughness becomes more of an issue. And that's why that's another thing that's specified. So, if we specify an X60 grade pipe, that means the pipe will have a yield strength of 60,000 psi. Is that right? At least, is the simple. It should. So these are minimum specified grades. So just because it says X60 doesn't mean to say that a particular pipe from that run is actually X60. It means it's a minimum of X60. And you might find, if you did tests on individual pipes, that one pipe was X60, the next one was X65, the next one was X70, then we had another X60. So the pipeline strength can vary, but none of them will drop below 60,000. So the pipe manufacturer accounts for variations in pipe strength due to variations in steel composition, plate rolling conditions, and pipe manufacturing conditions by actually trying to make a steel grade with a higher value on average of the properties and checks 3 standard deviations below the average to make sure that none of the distribution goes below the minimum value that's specified. Now it's impossible to make something that will be perfect, so there will always be the odd piece of pipe which won't meet the specification. But on average, when you sample the material, they should all be greater than that minimum yield stress. The maximum strength may be 120 megapascals more, or 17 KSI, or 17 X units higher than the minimum. So you get quite a distribution of properties. And this can be a problem, because if you're matching your welding properties to the properties of the steel, which one do you match it to? The minimum or the maximum? So that is an issue. So we have this idea that X60 can have some X77 in it, and when we want to weld this, what we want to do is overmatch the weld. That means we want the weld metal to be the strongest thing in the system, so that the weld doesn't fail, the pipe fails. So you don't do that based upon the minimum. So here's an example. So this curve here, the heavy curve here, is the pipe material. This is a shielded metal arc weld. It actually is stronger than the pipe material, but if you picked a part of the weld distribution down here and you picked a part of the pipe distribution up here, the weld would be weaker. This situation here, this case, the distributions are separate, and only in this little area here would you worry about overlap. So this one is correctly overmatched, and this is the one that you would specify. This one here is overmatched, but it's not correctly overmatched, and you wouldn't specify that. So you need to know the distribution of strengths to fully choose the correct set of welding parameters, because you want the weld to be stronger than the pipe for the best performance overall. So, what does a handbook value say? The yield stress of this steel is 555 megapascals. It doesn't say, and it has a distribution of 120 plus or minus 60 megapascals around that. You have to know that, you have to measure that, and you have to check that that is what you want. Or what you do is you say to the steel companies, I want a material that has got this minimum yield stress, and we're going to sample some of the things that you send us to check that you're within that specification. So as well as actually measuring things and specifying things, you have to check every now and again that the real material meets that specification. So how do we do that? Well, the standard test method for a piece of pipe is called the API strap tensile test. So you cut a section of pipe out, and you can see it's cut in the hoop direction around the pipe. And then you put it in a press and flatten it. And then you cut some restrictions on each side to form what we call the gauge length. So we machine it to the shape of a tensile strength test, and then we put it. So it's not the same as just machining it from bar stock. There will be some contribution from the fact that it was made into a pipe before you did that. Typically, the hoop direction is the main direction where you want to have the strength, because the pressure inside is trying to expand the pipe, it's trying to increase its diameter, and that's where the main information is. For small pipes, sometimes you can't do that. You've curved it too much. So then you can cut it in the longitudinal direction, but that's not so good. And what flattening does is actually reduce the yield strength that you measure. Because if you imagine bending something some way, you've actually put some plastic deformation in, you've created what are called dislocations, which are responsible for plastic deformation. When you bend it back the other way, the dislocations that you've already created can move in the opposite direction. They've already been created, you don't have to create them, they just have to be moved. And And its usual result is that the yield strength drops when you measure it in the opposite direction. So if you bend it one way and then bend it back, you will have effectively reduced the yield strength. And this is called the Bauschinger effect. So when a material is plastically strained in one direction, the measured yield strength in the opposite direction is reduced. And that's good because you're measuring the minimised yield stress, and if that still meets the specification, then the original one would have done. So we often just assume that this is an extra safety factor. But if your design is on the edge, and you don't want to be worried about whether this Bauschinger effect varies from sample to sample, and you want to really make sure that it works, then you might want to do a more complicated mechanical test. So in critical designs, you might have a more accurate measurement. But getting a more accurate measurement is expensive, so people don't tend to do it. So the other thing you can do is do a longitudinal test. So instead of from around the circumference of the pipe, along the length of the pipe, they don't need flattening. But because of the way that the pipe's been made, they measure a lower yield strength. So again, there is a problem with the data because it's not measuring in the direction of loading, and it will come out slightly lower. But again, if it's lower and it still meets the specification, that's probably all right. Sometimes you can cut from the pipe wall a round bar test piece, a much smaller test piece from inside the wall. You have to do a lot of machining to do it. And this usually results in a higher value of the yield strength when you do that, because it's not got all the surface defects from the pipe which are contributing to the behaviour you measure. But sometimes, for some designs, it's the only way you can get a decent sample that is reliable when you do the test. If you've got a heavily deformed pipe surface, it can be every measurement you take will give you a big scatter in results, and so you try to then pick more reliable tests just to check the basic material rather than to check the material and its manufacturing process, which is what we're doing with the API strap test. So a typical sample might look something like this. Round bar, gets a bit wider, and these bits near the end are used for the gripping mechanisms in the tensile tester, so sometimes they have threads cut in them, sometimes they fit into jaws and pull. The gauge length G, the bit in the middle, where the diameter of the bar is the same, that's the smallest part, so the stress should be concentrated in that area, and the test is valid if the failure occurs in that middle gauge length section. What happens if you have to test the whole pipe? Because you're absolutely critical and you don't want to have any Bauschinger effect questions in. Well, you do what's called a ring tension test. So you cut a whole ring, a whole hoop of the pipe, put it in the test machine, and then expand that and measure it. And that is the closest we can get to an absolute measure of the pipe behaviour. So that's a ring tension test system. So here's the pipe, and there are these gauges here that measure the diameter of the pipe to measure the strain, and then there's usually a cam-driven system in the middle here which expands that central part outwards to provide the stress on the system. Clearly that's a much more expensive test than the simple tensile tests, but you can do that. And what, of course, people have done is that they've compared the two to give you an idea of, what you would expect. So we've got ring tension test data at the bottom, and we've got flattened strap tests from the same materials at the top, and these are the different data points that we've got for different grades of steel. You can see going from X50 up to 85 or something like that. And if there was a perfect match, if they gave exactly the same results, then all the data would fall on that 45-degree line. See, it doesn't. Up to about X60, the scatter of data is such that you probably couldn't tell the difference between the two. But when we get in above that level, then you can see that the strength that's measured in the ring tension test is less, or it is different, it's distinctly different than you would have got otherwise. The flattened strip value is lower than the ring tension value. There's still quite a bit of scatter on those data points, so you can't predict the effect of the Bauschen effect on your results. All you know is, in general, it's on the safe side. Nothing falls above the 45-degree line, so that's pretty good. I mean, within experimental error, there are ones that are very close to that line, but there isn't very much to worry about that. So, in summary, for this lecture, the flattened API strap test specimens are mainly used because for the sort of grades up to about X60, they're pretty much identical to any other test. Round bar tensile specimens are often used for the highest grades because they're less susceptible to defects and things like that in the system, and those are the more brittle materials. And ring tension tests are reserved for the more critical systems where you want to know things very accurately, particularly in development work. And as we go to higher and higher grades of steel, they'll be more important because of the deviations from the strap results. You get a lot of information also by looking at the failures in these strap tests. So this is the end. These are the two pieces that have been pulled apart. This is the fracture surface, and they've been laid end to end so you can see them. And just by looking at that, you can see that down the centre of this steel pipe, there is a failure. There is a crack that's running through that. And this is caused by segregation bands in the parent metal layer. You may think that's a horrible failure. We can't have that. We must reject this. Actually, a thin band of segregation, which is in the plane of the pipe, doesn't affect the load carrying capacity of that pipe at all. And so generally, those are ignored. Although they look pretty bad. If you imagine the top part and the bottom part of the pipe carrying all the load, and there's just this one very thin line down the middle, which isn't. Yeah. And that leads into the question about cracking and toughness. What Dr. Euler will do at the next lecture is talk a bit more about this, but I put this picture up because I think it sums up everything we need to know. This is a Liberty ship, which was designed and built very rapidly from cheap steel during the Second World War to deliver basically foodstuffs and materials to the UK from the US to keep us alive. And they were built so quickly that nobody thought too much about the properties of the steel, and a goodly number of them failed in this manner where you got a crack that ran right through the steel of the ship and broke it in two. You can imagine a wave at each end supporting the boat and then nothing in the middle, and the whole weight of the boat then acts downwards. There's a bending stress, maximum tensile stress at the bottom, defect, and a crack runs up. So the toughness hadn't been taken into consideration, the strength had. So this was the right thickness of steel, the right loading conditions, but it couldn't cope with the defects that were present, and the toughness of the steel was not good enough. So we developed ways to look at how to improve steel toughness over the past 50 years or so. And Dr. Euler will say a little bit more about that in the next lecture. So that's where I'll start. Anybody got any questions? I'll happily take them. If not, thank you. And,